Hi everyone, I'm Alex, and today I'm going to be talking about how you design an injector for a liquid rocket engine. So getting started here, what is an injector? The main goal of an injector is just to get the propellants from the feed lines into the combustion chamber. And while it's doing this, it needs to mix the fuel and oxidizer together to allow for them to be combusted. And in order to do this, it atomizes the propellants, and we'll go into how it does that later. But by atomizing them, you're breaking up the fluid stream from the feed lines into actual droplets, individual droplets of fluid, which then are able to be combusted. Because as you can imagine, it's more difficult to light, a stream of something that a big stream of something on fire than it is just a tiny droplet of the fuel that are all mixed together. So there's two main parts to an injector, and these can either be separate parts physically or combined together into one part. There's the manifold, which takes the fuel and oxidizer from the feed lines and distributes them to the correct channels on the injector plate. And the injector plate is what actually faces the combustion chamber of the engine, and it has some sort of set of orifices or channels in it which guide the fuel and oxidizer in specific geometries so that they mix when they enter the chamber. So some of the different types of an injector, these are the three main types that you'll see in anywhere from amateur to a big NASA or SpaceX rocket. The simplest to design and the one used by most amateur teams is an impinging injector. And so this consists of a fuel and oxidizer that go through these little tubes in the injector plate. And the tubes are at angles so that once they enter the combustion chamber, they converge at a specific point. And once those two fluid streams meet at that point, they atomize together because they have so much velocity. And there's various different types of impingement geometries, which I'll get into later. And the efficiency of those really depends on your specific feed system, what pressures you're running at, and the mixture ratios you have, and the actual specific propellants that you're using. Next is pintle. Some collegiate teams will use a pintle design. They're slightly more efficient than impinging, but also not too difficult to make. And they feed one propellant through a central tube, as you can see here. One of them is marked liquid, one of them is marked gas, but in reality, those could both be liquid. And one propellant, that the liquid here, goes through a central shaft, and it's traveling axially down the engine, but then it hits the pintle tip, which converts all that forward momentum into a radial flow. So it's moving towards the chamber walls, and then as it's moving towards the chamber walls, it hits the other propellant, which is still moving axially down the engine. And so those two streams impinge and atomize from there. And then there's the coaxial swirl design. I believe it's used in the Raptor engine from SpaceX, and maybe the Merlin one as well. And this is very different from the previous two in that it swirls the propellants before they enter the chamber. And so to do this, you inject your propellants tangentially. And so they form sort of a vortex in the injector plate. And then as those vortexes exit the confined space of the injector, they expand in sort of a hollow cone-shaped spray. And you can either have these sprays rotating in the same direction or in opposite directions. And once they enter the combustion chamber, these two cones of spray will hit each other. And because they have such a complex velocity, they're rotating, they're traveling in that cone shape. So usually the cones are at different sort of angles with respect to one another. And so they mix very efficiently, but they're also incredibly difficult to manufacture. And here is just sort of the general efficiency comparison between the three injector types. That diagram on the left is a pintle injector, by the way. So the combustion efficiency of rockets can vary depending on what injector type you use. Usually, for an impinging injector, you're getting anywhere from 94 to 97% of your theoretical maximum efficiency. And like I said, they're the easiest to design and still pretty efficient, especially if you get it up towards that 97%. So, very reasonable choice for a lot of amateur teams. And you should note that you cannot throttle them very well. So that's when you change the flow rate of your propellants to either reduce or increase the amount of thrust you're generating. They're not very good at that because you optimize your impingement angle and everything for a specific mass flow rate. And then there's the pintle design, which is anywhere from 96 to 99% efficiency. And so, as you can see, they're very efficient, slightly more difficult to manufacture, and they're very good for any throttling designs. And then coaxial swirl is by far the most efficient, and you can really get almost exactly at your theoretical maximum efficiency with that. But as I mentioned, they're very, very difficult to actually make, and they're difficult to throttle, but it can be done. So going into impinging injectors, and this is the only one I'll go into a lot of detail on because this is the one that we have mainly used as a team. So a few best practices starting out, and these are just from people's experience in the field experimenting with different injector types. Your pressure drop across the injector, you need a pressure drop to force your propellants into the chamber. And that pressure drop should be about 20% or slightly higher is fine of your chamber pressure. So if your chamber pressure is, let's say, 500 psi, then your pressure drop should be 100 psi. And then the orifice length, so that's the length of the channels that guide, the angled channels that guide the propellant into that impingement point. And that orifice length should be at least 5 times the diameter of the hole. And that's in order to ensure you have fully developed flow in the orifice. So when the propellant exits the orifice into the combustion chamber, it's traveling in a predictive way and is able to impinge well. And then your impingement distance, so that's the distance from the impingement point in the chamber to the injector plate, essentially how far your propellant stream is going to travel into the chamber before they impinge. And that should be anywhere between about 3 to 7 times your orifice diameter. And again, that's just found from experimental results. And usually a larger number of small holes is better because your propellant streams are already smaller, so they're easier to atomize. But there's sort of a limit on that based on your manufacturing ability if you're 3D printing versus CNCing it. And so that really dictates how small your holes are able to get in your injector face. And on the right here, you can see in this picture the impingement point, and then there's the ligaments are after you hit the impingement point, the fluid streams start to separate into not yet small droplets, but sort of just longer broken up pieces of fluid. And then these further break up into tiny droplets later on. And the measurements of those are important when you're actually doing CFD on your injector and predicting your combustion efficiencies. How long your combustion chamber needs to be to ensure that the ligaments have time to be broken up into droplets, and those droplets have time to combust. And so, again, there's not really any universally accepted equations for those things. There are some research papers that have proposed methods on predicting them for various types of injectors, but there's not really one accepted way to do it. And the best way is just from a very accurate CFD simulation, or even better is just real experimental results. So going into how you actually size the holes in your injector face for an impinging injector, you can use this equation, the m dot equation there on the left, for sizing, and that's if you use the mass flow rate for, let's say you're just trying to find the orifice size for your fuel. So if you use the total mass flow rate for your fuel, that'll give you the total area on your injector face of all the holes for fuel combined. Or if you say have 10 injection holes for fuel, you would divide your mass flow rate by 10 and use that to find the area of one specific hole on your injector plate. And in that equation, rho there is the density of your propellant, and delta P is the pressure drop over the injector. I should note that that equation only holds true for incompressible flow, which is usually the case if you're dealing with liquid propellants. If you have, let's say, one of your propellants, your oxidizer, is a gas, then you'd have to use compressible flow equations to find the orifice size. Not too complicated, but it is a different equation. And then the CD there, that's the discharge coefficient, and that's dependent on the actual geometry of the hole and the geometry of the channel leading into the hole. And that usually varies between 0.7 and 0.9. There are extremes where it can be lower or higher than that, but there's no equation to calculate that. You can get a pretty good idea from CFD, and there are some tables which have an okay starting point, I would say. But to really nail that down to get a precise value, I recommend doing cold flow tests, and then you can optimize your injector after some cold flow tests and sifting through that data. And then on the right here, you can see one of those tables I mentioned for estimating CD based on your different hole properties and different geometries leading into and out of those orifices. So next, the next main measurement to nail down here is the injection angle. And so this is the angle that the fuel and oxidizer are injected relative to the axial direction. Some papers might do it relative to the radial direction, so it's important to figure out which convention whatever you're looking at is using. But for this, I'll use the axial direction. And the goal of your impingement is to have, in the bottom right diagram, the variable beta, that's your resultant flow angle, and you want that to be pretty much 0 so that your combustion, your streams and ligaments and everything of the fuel and oxidizer are traveling axially down the engine. And that means that you're going to have the most efficient momentum as you start expanding that in the nozzle. And then there's two main different types of impingement. There's like impingement, which is when you have two of the same propellant injected at an angle and they impinge together. And that's nice because it simplifies some of the math. The impingement angles should be the same because both fluid streams will have the same momentum. And then, once they're the same, that your resultant flow angle will be 0 based on that. And that holds true even if you have something like a triplet impinging design where you have, let's say 2 fuel lines injected at an angle that impinge at a point, and then one oxidizer line that's just already traveling axially between those 2 fuel holes, and then that's also goes through the impingement point, and so they all 3 converge in the same point. And that's the design that we used for engine alpha and engine beta. It's one of the more efficient impingement designs. And then for unlike impingement, that's the case where if you are injecting your fuel stream into your oxidizer stream, and so because those will have different mass flow rates and different densities, they have different momentums. And so the equation on the right there allows you to, you set beta equal to 0, and then you can solve for your injection angles based on that, and that helps to balance your momentum so that your resultant is actually traveling axially out of the engine. And then some other things to consider is that the injectors can only be so big. You can only have so many holes on them because you're limited by the size of your combustion chamber. For small engines, you can sort of increase your contraction ratio in your engine to make the chamber big enough to have a big injector, but that's not super efficient, and so you'll see a lot of professional engines. The injectors are very restricted by the design of the combustion chamber. And then when you design the manifold, so like I mentioned, that can either be a separate piece, which is the case if you're milling the parts, because otherwise you wouldn't be able to manufacture the inner channels there. Whereas if you're 3D printing it, the manifold and injector plate could be all one piece. But if they are two separate pieces, you have to take care to seal the different propellant channels off from each other, because you don't want your oxidizer and fuel mixing in the injector before they enter the chamber. That'll lead to some combustion instabilities and also the risk of your injector blowing up and potentially your feed lines blowing up as well. So that's very bad. And then no matter what your design for the injector is, you have to attach it to the combustion chamber in some way. And so you need to use high temperature gaskets or O-rings, depending on your design, or both for double redundancy, to seal the injector plate to the combustion chamber and prevent any of those hot combustion gases from escaping. And that could lead to an explosion as well. So obviously bad. And then you have your spray pattern. And so that's when the two impinging jets hit each other. The resulting spray has a certain geometry to it, and you want to minimize the amount of that spray that ends up landing on your chamber walls, because that will lead to combustion on your chamber walls, which will add a ton of heat into the walls, which will make it difficult to cool your engine and could lead to an explosion as well. And that's best verified just through CFD software to see how the mixing occurs after it exits the injector. So that's all I have for injectors. Thank you for watching, and please email me or talk to me in person if you have any questions. So thanks for watching, and good luck designing an injector.